So now that we have talked of all these things, we have talked about overvoltages, the likelihood of overvoltages, what kinds of overvoltages. We've also talked about the insulation characteristic, and the insulation characteristic is your insulation breakdown probability. Now, present-day approach for insulation coordination is statistical in nature. Now, if we look at this figure, this is the overvoltage distribution. This also has a kind of bell-shaped curve. As I said, many of the events that we see around us can be expressed, can be used, do have a bell-shaped distribution. So this curve one is an overvoltage distribution. So therefore, as you see, the probability of certain overvoltages is pretty low. Then you have some central values where the probability is pretty high, and this is probability. This is not cumulative probability, but probability. So if you are talking about this particular value, so if you're talking about this particular value of voltage, so the probability of this particular value, let's say Vi, the probability of this overvoltage V naught is given by this probability, whatever that value is. So maybe 20%, and not 20%, it will be higher than that. So maybe 60% or something of that sort. So this is the actual value of a particular overvoltage occurring. An overvoltage of, let's say, 20 kV. And that may have the same probability as another overvoltage, let's say, of 60 kV. And then there might be some values like 40 kV, which are much more likely. And then they taper off at both ends. So there is a certain value of overvoltage which is likeliest, and there are a distribution of overvoltages on both sides of the central value. Ultimately, they can become zero at very low voltages. I mean, you don't have overvoltages lower than a certain value and higher than a certain value. So this is the particular value of the overvoltage that occurs. And then I have a second curve 2. This curve 2 is the insulation breakdown probability. And as we have discussed, we are interested in withstand at a particular voltage, which means that should also encompass the probability of failure at voltages lower than that, and therefore the insulation breakdown probability is expressed as a cumulative distribution function. So when I talk about this particular value, let's say Vk intercepts the overvoltage curve at this value P0 Vk, which means P0 Vk is the probability of occurrence of an overvoltage with exactly magnitude Vk. So the probability of occurrence of an overvoltage Vk is given by P0 Vk, and that is the exact value of magnitude of the wave, actual magnitude of the overvoltage that occurs, nothing less, nothing more. At the same time, this Vk, if you take it from the probability breakdown probability curve, this PBVk is the probability that the gap will break down at voltage Vk. And that is the cumulative probability. The cumulative probability that if you apply a voltage Vk, the gap or the insulation will break down. It might break down at voltages lower. It might break down voltages exactly equal to Vk, but this is the probability that when you apply Vk, it will have broken down. So one is a real probability and the other is a cumulative probability for the physical reasons that I have just mentioned. Now, what would I like to know? I would like to know, I have a gap, this insulation. It can be a gap, it can be some dielectric material, and I want to figure out what is the probability that it will break down. Now, when will it break down? Depending upon the insulation characteristics, there is a probability or there is a cumulative probability that it will break down at a voltage Vk. But having said that, Even if that probability is 100%, breakdown will not occur unless I apply an overvoltage VK across it. So air breaks down at 30 kV per centimeter. But even the probability of breakdown of air at 30 kV per centimeter will be 0 as long as the probability of me applying a voltage 30 kV on a 1 centimeter air gap is 0. So therefore, for a gap to break down, two things need to happen. First is I need to know what is the probability of its breakdown. That probability of breakdown at a particular voltage VK must not be 0. It should have some value. And there should be an overvoltage of magnitude Vk. So the probability of breakdown, probability that the gap will break down at a voltage Vk is given by the multiplication of PB Vk into P naught Vk. Du is a very small, so I'm going to try and calculate. This is an area, so this small infinitesimal area around Vk is represented by PBVK, P naught Vk du, if I consider these voltages to be continuous. If it is a discrete value, then of course it's PBVK into P naught Vk. So probability that overvoltage of Vk occurs multiplied by the probability of breakdown at that overvoltage. That is given by PBVK, P naught Vk. This product into du gives me the area under the curve in case my voltage is continuously varying. So an infinitesimal gap, infinitesimal width around Vk, and this dotted dashed region expresses the probability which is given by the area under this dashed rectangle. So therefore, if I am working with an insulation which has this insulation breakdown characteristics and this is my overvoltage distribution, what is my total risk of failure? My risk of failure, if you remember, we said at the outset that my insulation coordination will aim at obtaining the risk of failure, and this risk of failure is defined as the total probability of failure of your insulation or gap given this overvoltage distribution, and therefore this must be this total area under the curve here, which is given by integration of this probability, the probability that breakdown occurs at Vk is given by PBVK into P naught Vk du, and the total probability of failure is given by the integration of this quantity from 0 to infinity, from the entire region from 0 to infinity. Now, of course, here, beyond this value, the probability of overvoltage happening is not 0, but at these overvoltages, probability of breakdown, insulation breakdown is 0. So this quantity, this product will be 0. Similarly, beyond B, the insulation breakdown probability is very high, but the probability of any overvoltage above this magnitude happening is 0. So again, the product will be 0. So we don't really need to take the integration from 0 to infinity. We only need to integrate from this point A to this point B. And that integration gives me the area under the curve R, which is shown by this hatched region. And this hatched region is your risk of failure. So to repeat, I can estimate the risk of failure by quantifying the total probability of failure at a random voltage Vk. The probability of failure of insulation at voltage Vk is given by the product of the cumulative probability of failure at Vk multiplied by the probability of an overvoltage of magnitude Vk occurring, and by integrating the total area under this product curve, I obtain my risk of failure. Now, if I want to reduce my risk of failure, I should reduce this area. This hatch region should decrease in size. How can I decrease the size? I can decrease the size by decreasing the AB region, by decreasing the overlap region between my overvoltage distribution and my insulation breakdown probability, I would be able to reduce the risk of failure. So let us talk about a statistical overvoltage. The statistical overvoltage is defined as that value of the overvoltage such that probability of occurrences of overvoltages of magnitude Vs or higher is only 2%. So this is your probability distribution curve for overvoltages, and Vs is a quantity, is a magnitude of Vs such that the area under this probability curve on the right hand side of Vs is only 2%. In that case, Vs is the statistical overvoltage. So by definition, the statistical overvoltage is that value of the overvoltage Vs such that the probability of occurrence of overvoltage of magnitude Vs or higher is only 2%, and it is given by the shaded curve. Similarly, we can define a statistical Wheatstone voltage, which is given from the cumulative probability distribution curve. The statistical Wheatstone voltage Vw is such that only 90% in 90% of applied impulses, breakdown does not occur, which means only in 10% of the cases breakdown occurs. So this is your cumulative distribution function, and somewhere near the beginning of this curve, the cumulative probability distribution might be very small, so 10%, so that's 0.1. So if this value is 0.1, that means if you apply voltages equal to VW or less, the probability of failure is very low, only 1%, and the probability of withstand is very high. In case of non-self-restoring insulation, the electrical withstand is expressed in terms of actual breakdown values. This is an important distinction to make. Now, we have different kinds of materials. We have self-restoring insulation. Self-restoring insulation, if it breaks down, we just have to wait for a sufficient amount of time and it will regain its dielectric property. And then we have, these are mostly gases. And then you have liquids which will need to be changed once discharge happens. And also in case of solids, you have a situation where there will be permanent damage if breakdown happens. So in that case, we will not bother with 1% or 2%, etc. In case of materials where the insulation is non-self-restoring, so that if breakdown happens, a permanent damage occurs, then the withstand voltage is the actual breakdown value. So the actual breakdown value could be a value that we establish to be, like, say, 50% of the time breakdown happens, but we would work with the breakdown strength of the material and we will not work with the 10% breakdown value. We will work with the withstand value is the actual breakdown value, and how we determine the actual breakdown value will come from testing. We will discuss that in testing. So, but for air gaps or self-restoring insulation, the withstand value is the 0.1 value. Now, as I said, we also define something called the statistical safety factor, which is given by gamma is equal to VW by Vs. So it is the ratio of the withstand voltage to the statistical withstand voltage to the statistical overvoltage. This gives a measure of how risky the scenario is. If you look at these three cases, you have Vs and you have Vw. In this case, Vs is taken to be Vw. So gamma is equal to 1. If Vs is equal to Vw, this is the kind of risk of failure that you can visually see. Now, if you now make Vw to be equal to 1.2 Vs, so I'm increasing my statistical safety factor. If I increase the statistical factor, this is equivalent to moving the insulation curve to the right. So I'm displacing, compared to this first figure, PB curve is now displaced to the right. As a result, the intercept region has decreased, and therefore the risk of failure has also decreased. Similarly, now you increase it further. So you have 1.4, the risk of failure has decreased further. So therefore, the risk of failure gives me a probability of failure. I would like to decrease the risk of failure. To decrease the risk of failure, what I need to do is I need to increase the statistical safety factor. But remember, increasing the statistical safety factor will reduce the risk of failure, no doubt about that, but at the same time, it will also cause an increase in the insulation cost. So you will have to exercise an engineering judgment as to how much risk of failure you will accept as a acceptable value. If you remember, we said at the outset that insulation coordination does not aim to eliminate failure, but only tries to limit the risk of failure to an acceptable value. So who decides the acceptable value? That will come from engineering judgment. That will be a matter of the design in hand. But we do know how to decrease the risk of failure, and that has to be done by increasing the statistical safety factor. Similarly, we can also talk about this thing can also be applied while deciding the protection levels and the protective margins. This is your insulation. Your protecting gap of the protecting device will have a similar cumulative distribution, and obviously it should be to the left of the insulation curve. So if this is your overvoltage distribution, then somewhere on the decreasing slope we have the insulation curve, so that gives me the risk of failure. Whereas remember, for the protective gap, where the risk of failure of the gap breakdown should be very high, and therefore that will be somewhere to the left of your overvoltage, so that most of the overvoltage is prevented from reaching the insulation and causing damage. So look at the risk of failure of the protective gap. The risk of failure of the protective gap is the entire region under this dashed line, dashed curve, so, and this hatching. So this is a very large probability, a very large risk of failure of the protecting gap. But the protected gap is this double hatch region, which has a very small risk of failure. And the difference between these two values, the PW here and the PW here, is the margin of safety. So here we are not working with volt time characteristics, but we are working with probability distributions, and that is the more modern way of doing here. In general, we should remember that the volt time characteristics can also be important, and that has to be taken into consideration. The time probability also has to be taken into consideration. So probability that the gap will operate is much higher than the probability of insulation damage or failure. In general, gap will break down well before the insulation even reaches its highest over voltages. So before we come to this peak value, the gap needs to break down. That is required. So these are the references that I have used for insulation coordination.